In this particular lesson of radical functions, we are going to be evaluating nth roots. So as we looked at in the prior lesson, we went back and forth converting between radical form, the fifth root of 7 squared, and rational exponent form, 7 to the power of 2/5. Remember, the root is what's inside the little hook of your radical symbol. That's called your index, and it becomes the root or the denominator of the fraction. The power of your base, 7 to the second power, becomes the numerator of that rational exponent. So just a quick little warm up. Simplify without using a calculator. See how much you remember. How do you simplify your square roots? So the square root of 24, you got a couple of different ways. Some people like to look at things that multiply to 24 and say, oh, hey, that would be 2 times 12. And 12 would be the same thing as 2 times 6. And 6 would be the same thing as 2 times 3. And then you find the pairs that you have, because a square root means the same thing times itself, or multiplied by itself. I have one pair of 2's, so that factors out, and the other things that are left get multiplied back underneath. Another way you could look at that particular example would be this 24 could be 4 multiplied by 6. So that would be like the square root of 4 multiplied by the square root of 6 separately. And the square root of 4 simplifies to be 2. The square root of 6 we don't know, so it's just 2 square root 6. So whichever way you like is the way that you get to use. All right, our next example, 98k is under the square root. So I'm going to look at things that multiply to give me 98, definitely even, so I'm going to start with 2. So 98, and normally I would look for a perfect square, but I'm going to start like this. So half of, that's really close to 100. Half of 50, or half of 100 is 50, so that would be 2 less, so half of 49. So 2 times 49 gives me 98. And then 49 is a perfect square, 7 times 7. So I can take the square root of 98 to give me 7 square root 2. Now you need to look at your variable. If the variable has a power of the index or greater, then it can be simplified. This is k to the first power. So remember, if we rewrote it as a rational exponent, that would be k to the power of 1/2. That does not simplify, so we're going to leave that one under the radical. So the square root of 98k simplifies to be 7 multiplied by the square root of 2k. And our last example, 392k squared, take its square root. Okay, so here's an example. I want to show you the variable part first. K squared, remember I'm taking the square root. That would be k to the second power divided by 2, which means I've got a pair of 2k's, so I could take its square root just to give me 1k. So I will have a k on the outside of the radical symbol. Now let's do the work for 392. This might take a little bit. So 392 definitely divisible by 2. And again, I would rather look for a perfect square. It'd be a little bit easier. So 392, 2 divided by 2 would give me, let's see, 92 divided by 2 would give me 4,600 and, so half of that would be 46, half of 300 would be 150. So those together would be half of 392 is 196. Still even, divide through by 2 again. Half of 96, that's really close to 200. So that would be 98. Oh, we just did the square root of 98. That is 2 times 49, which is 7 times 7. So I'm going to factor out all of the terms that I have a pair for. I have a pair of 2's, 2, and a pair of 7's, multiply by 7, multiply by the k, and only the 2 is left under the radical. So I get 2 multiplied by 7 multiplied by k times the square root of 2, which simplifies to give us 14k square root 2. Kind of took the long way to get there, guys, but hey, whatever works for you. That is the square root of 392k squared. All right, what about simplifying a cubed root? You can do the same thing that we did for the square roots, but this time we want triples. So I want 3 of the same thing. So let's look at the factors of 24. We did that already. That would be 2 times 12, which is 2 times 6, which is 2 times 3. So in this case, the root tells me how many that I need for each group. So I need a group of 3. I have a group of 3 2's, one group of those, and the number left would stay under, in this case, the cubed root. Now I'm going to look at the m to the third power. You got a couple choices. I can say m cubed is the same thing as m times m squared, which would be the same thing as m times m. So I do get a group of m's, so an m can come out. You can do it that way. Or you can write it in exponential rational exponent form. So m to the 3/3, the power over the root, which simplifies to be m to the first. So the cubed root of 24m to the third is 2m multiplied by the cubed root of 3. So you can take cube roots as well, not just square roots. All right, so our notation for a square root is just a regular radical symbol. If you ever see the 2 inside the hook, it means the same thing. The cubed root puts a little 3 for the index, or a 3 inside the hook of the radical symbol, and the 4th root puts a little 4, and so forth as you continue on the pattern. If I said, what is the 100th root of something? So the 100th root, that would be a 100 inside the little hook of the radical with whatever term goes underneath. Okay, so the square root, what does that mean? How do you evaluate, and how can you rewrite it as a rational exponent? It means the same number multiplied twice to equal 25. Okay, now we know this. You guys have been doing this forever. The square root of 25 would be the square root of 5 squared, 5 times 5. So if I have a square root of something squared, they undo, just leaving me with 5. Again, if we want to rewrite as a rational exponent, this is 25 to the first power, and we're taking the second root, or the square root. So that would be 25 to the 1/2 as a power, which again will simplify to be 5. But we want the rational exponent form. Okay, the cubed root of 64 means what number multiplied how many times? That's right, multiplied 3 times equals 64. So we can evaluate, think about things that multiply to give me 64. Okay, so a lot of us are going to go 8 times 8, but remember I can break those down even more. Okay, so let's start with 2. So 64 divided by 2 is 32. Still even, I can divide that by 2 to get 16. Still even, I can divide 16 by 2 to give me 8. Still even, I can divide that by 2 to give me 4. And one last time, 2 times 2 gives me 4. So I'm looking for what number multiplied by itself 3 times, or if I want a cubed root, I want how many groups of 3 of the same number do I get? So I've got 1, 2, 3, 4, 5, 6. Cool. So I've got 2 of those. That's awesome, which means that I can have the cubed root of 64 equaling the cubed root of, there's a group, there's a group, and there's a group. 4 multiplied by 4 multiplied by 4, or the cubed root of 4 cubed, which you would see would undo itself, just leaving me with 4. And if I want it as a rational exponent, the cubed root of 64 to the first power would be rewritten as 64 to the power of 1/3. Okay, and just to kind of clear this up again, guys, remember we're looking for groups that will multiply through to work for us. So as I'm looking through each of those, I found 2 times 2 and 2 times 2 and 2 times 2. Okay, so a 4 times a 4 times a 4, that's where that came from. I didn't know if, hopefully that didn't confuse you guys as I was writing all that stuff out. All right, the 4th root of 81 means what number multiplied 4 times equals 81. question mark. If we evaluate, I want to have the same thing multiplied by itself 4 times. So I know that 81 is divisible by 9 and 9. Okay, and 9 and 9 are both divisible by 3, so let's start with 3. 81 divided by 3 gives me 27. 27 is divisible by 3, which gives me 9. And 9 is divisible by 3, which gives me 3. Okay, so I have one group of 4 3s. So 4 to the third equals 81. Or excuse me, I wrote that backwards. So sorry. I totally wrote that backwards. It's 3 to the 4th power. Forgive me. Erase that and fix that, guys. All right, so if I want the 4th root of 81, I could rewrite that as the 4th root of 3 to the 4th power. The root and the power would undo, and that would just leave me with 3. And as a rational exponent, it would be 81 to the power of 1/4, which does have a value of 3. So it's 3 multiplied by itself 4 times to give me the 81. All right, now we're going to practice these with variables. They're going to mean the exact same thing. If you need to write them all out, you 100% totally can. As the powers under the radical get larger, it takes a little bit more, so try to find yourself a few more tricks if you can. So our first example is the square root of x to the 5th. That means I have 5 x's multiplied under the radical, and I want groups of 2. I want pairs. So there's 1, so an x is factored out. There's a second group, another x is factored out, and this lonely little dude stays by itself under the radical symbol. So it's x multiplied by x by the square root of x, which does give us x squared multiplied by the square root of x. Okay. One way you could do the cubed root of m to the 6th would be the same way. Write out 6 different m's, and in this case, find groups of 3. Okay, so if I'm looking at 6 m's under the radical, I've got one group of 3, 2 groups of 3, so I can have an m multiplied by an m, and I don't have any leftovers, so that would just give me m squared. If you ever want to turn it into a rational exponent, this would be m to the 6th third power, and 6 divided by 3 to simplify to give us m squared. So you kind of got both ways in order to simplify these. The 4th root of y to the 11th. All right, let's count by 4s and not write 11 y's out here. So I can have y to the 4th and another y to the 4th. That would give me y to the 8th. Multiplied by a y, 8, 9, 10, 11, I need y to the 3rd. And I'm going to take the 4th root of each of those. The 4th root of y to the 4th gives me y. That's one group of 4. The 4th root of the other y to the 4th gives me another y. And the 4th root of y cubed does not simplify, so it stays under your radical. This would finally give me y squared multiplied by the 4th root of y cubed. And last but not least, the 5th root. Count by 5s. Okay, so if I count by 5s, I've got 5, 10, and then 15. So I can definitely get to 10. So I'm going to write this another way, is I could write it as w to the 10th times w to the 4th. And if you wanted to write that as a rational exponent, that would be w to the 10/5 multiplied by w to the 4/5. 10/5 would simplify to give you w squared, and the 4/5 doesn't, so that would be w to the 4/5. That answer would be perfect in rational exponent form. If we wanted it in radical form, we would convert. The w squared would stay outside, and we would take the 5th root of w to the 4th. So you kind of have a couple of ways that you can do these. The other thing you could do is you could have continued to simplify and written the 5th root of w to the 5th, w to the 5th, and w to the 4th all under the radical, and recognize I have one group of w's, of 5 of them, a second, so that would get multiplied outside, and then the w to the 4th would have to stay under. which again gives us that same solution, w squared multiplied by the 5th root of w to the 4th. Now we're going to mix them up, change them up, move them all around. The square root of 16 x to the 4th. You know the square root of 16. The square root of 16 is 4. The square root of x to the 4th, remember that is the second root. I'm looking for groups of 2. X to the 4th would be an x squared multiplied by an x squared. So I got 2 groups. There you go. So that just simplifies to give me an x squared. Again, you can always take x to the 4th divided by that root or that index, and it will simplify to give you what reduces out. Our next example, the cubed root of 27m to the 7th n squared. Remember, if the power is smaller than the root, it won't simplify, so that will stay under the radical. So the cubed root of 27, 3 multiplied by 3 by 3. So this would be the cubed root of 3 cubed. Then I can write m to the 7th as m to the 6th and m to the 1st, because 6 is divisible by 3. The n squared I leave the same. The cubed root of 3 cubed is 3. The cubed root of m to the 6th would be m to the 6 thirds, gives me m squared. This lonely little m stays under the radical, and the n squared does as well because it does not simplify. So this would be 3m squared multiplied by the cubed root of m n squared. The 4th root of 256, w to the 4th, x, y to the 6th. Remember, that lonely little x has x to the 1st. It's a smaller root, smaller power than the root, so it won't simplify. The 4th root of 256, 4 times 4 times 4 equals 64 from a previous example. If I multiply that through by 4 again, I will get 256. So I can write 256 as 4 to the 4th power. And then I'll keep w to the 4th, x, and y to the 6th. Simplifying, the 4th root of 4 to the 4th power, those would undo each other, leaving me with 4. I had 4 groups. W to the 4th, take its 4th root, leaves me with a w. Remember, that would be w to the 4 fourths. X to the 1st doesn't reduce, so that guy is going to stay under the radical. And y to the 6th, I could write that as y to the 4th and y squared, and then I could simplify the 4th root of y to the 4th, so a y comes out, but I have a y squared left under the radical. And the last example of this set, the 5th root of 32y to the 25th. Let's start with 2's. 2 times 2 is 4, times another 2 gives me 8. 8 times 2 is 16, and 16 times 2 is 32. There you go. So 32 is the same thing as 2 to the 5th, and then we have y to the 25th power, and we're taking the 5th root. I'm going to show you writing these with rational exponents. So 2 to the 5/5 power multiplied by y to the 25/5 power. Each of those exponents simplify. 5/5 reduces to 1, so 2 to the 1st power is just 2, and 25/5 reduces to 5, so it would be y to the 5th. So again, you've got a couple of different ways you can look at these. Whichever way makes the most sense for you is how you should always continue to process. And keep asking your questions and making sure that you are getting all of it as we go through. All right, we never, ever, ever, ever leave a radical in the denominator of a fraction. So we are going to multiply the numerator and the denominator by whatever is in the denominator. And in this case, it will always be a square root or a cubed root or something like that. Okay, so our first example is the square root of 1 over 3x. I'm going to simplify this to be the square root of the numerator divided by the square root of the denominator. Now we know the square root of 1 is just 1. So if you'd like to go ahead and simplify that, you can. So it'd be 1 over the square root of 3x. The square root in the denominator is a big no-no in mathematics. So we need to multiply by its square root, the exact same thing, because a square root multiplied by itself will undo itself. So now I have 1 multiplied by the square root of 3x, which is just the square root of 3x, And then in the denominator, when I multiply the square root by itself, I'll get the square root of 9x squared. You do not really have to show this step. You can jump to the final solution. This would be square root of 3x over the square root of 9x squared would just be 3x with no radical left. There you go. We have a few more of these to practice and then we'll be done. The square root of 2x cubed over x to the fourth. So I'm going to simplify this to be the square root of 2x cubed over the square root of x to the fourth. Our denominator actually simplifies already, so in this case we don't need to rationalize. The square root of x to the fourth would be x to the 4 halves, which is just x squared. In our numerator, I can simplify x to the third power because I've got one group of 2, so I've got an x squared times an x. So the square root of the x squared is just x. The other guy has to stay underneath the radical with the 2. So it's x square root 2x over x squared, and I now can simplify the x over the x squared to just leave me with the square root of 2x over x. No radicals in the denominator. Good deal. Our third example, the cubed root of 8x to the fifth over 4xy squared. In this case, I need every term to be raised to the third power. So I need to multiply through by the denominator, but make them the third power, okay? So I'm going to separate out first like I've done for each of the others, the cubed root of 8x to the fifth over the cubed root of 4xy squared. So I need to look to see what would I multiply by so that it will be a perfect cube. Well, I know that 2 times 2 times 2 gives me 8, and that's the same thing multiplied by itself 3 times. So I could multiply by the cubed root of 2 so that the 4 times the 2 would turn into an 8 and simplify. And then I need an x times an x times an x to give me an x cubed. I have x to the first. I need 2 more of them, so I'm going to multiply by the x squared under the radical. And the last term I have a y squared, so I need to multiply by a y so that all those exponents will add together and work out for me. So I'm going to multiply by the cubed root of 2x squared y in each numerator and denominator. Here we go. In the denominator, we will have the cubed root of 2 times 4 is 8, x times x squared is x cubed, and y squared times y is y cubed. Our whole goal for that was for it to simplify to be 2xy, common integer terms and variables with integer exponents. In the numerator, we're going to have the cubed root of 8 times 2. I'm just going to go ahead and list those there. And then x to the fifth times x squared, so that would give me x to the seventh, and then just a y. The reason I left the 8 times the 2 is because we've already taken the cubed root of 8 in the denominator, so I know that part simplifies just to give me 2. That does leave me with a 2 under the radical. X to the seventh, that could be x to the sixth multiplied by x to the first, and I can take out groups of 3 from x to the sixth. I can take out 2 of those, so that would be an x squared, leaving me with 1 underneath, and then I still just have that lonely little y. So I have 2x squared multiplied by the cubed root of 2xy all over 2xy. Now let's look to see what reduces. 2 over 2, good. And x squared over x, I can reduce an x in both numerator and denominator, and the y will stay there. So our final simplification of this leaves me with just an x in the numerator, the cubed root of 2xy all over y. That one was really kind of beefy, wasn't it? Sure was. All right, in our next example, we're going to be taking the fourth root of each of these terms. It's already been written out in that manner for me. The fourth root of 32, x to the 8th, and the fourth root of 2x to the 9th. I already see that I can simplify x to the 8th, that fourth root of it, but I'm going to show you something else first. So let's put it back in a big giant ugly fraction. 32x to the 8th over 2x to the 9th. In this case, I can simplify the 32 over the 2. That just gives me 16. And x to the 8th over x to the 9th leaves me with an x in the denominator. Let's see what we can simplify from here. What is the 4th root of 16 over the 4th root of x? Well, the 4th root is 16. 2 times 2 is 4, times another 2 is 8, times a last 2 is 16. So the 4th root of 16 is just 2, and that leaves me with the 4th root of x. Okay, that one's not completely done. Tuck around and follow me down here. I need to multiply through in both numerator and denominator by the 4th root of x cubed. Okay, think for a second, why am I multiplying by the 4th root of x cubed? Remember, we're trying to get that denominator to be raised to a power of 4 or greater underneath, so it will simplify. So I want it to be a 4th power, an 8th, or a 12th, one of those multiples. So the numerator is going to be 2 multiplied by the 4th root of x cubed. Denominator is now the 4th root of x to the 4th, which simplifies just to give me an x for the denominator. So our final simplification of that last example is 2 multiplied by the 4th root of x cubed all over x. We do have some special rules for odd roots, like the cubed root and the 5th root and the 7th root, as well as for even roots. So our odd roots are only going to have one real root. It doesn't matter if I'm taking the cubed root of 8 to give me positive 2, or the cubed root of negative 8 to give me a negative 2, because 2 times 2 times 2 gives me the positive 8, and negative 2 times negative 2 times negative 2 does give me the negative 8. However, for the even roots, we're going to have a couple of different rules. If the value of the number underneath the radical is greater than 0, in other words, if it is positive, then you're going to have two real roots, both a positive and a negative. If it equals 0, then you will have one root. And if it's less than 0, in other words, if it's negative, then you are going to have 0 real roots. Remember, we did these a while ago. These are going to be your two imaginary roots. Keep that in mind as we go through the following examples. All right, so we're going to evaluate the 5th root of negative 32. This is an odd root, so we will only have one answer. Since it's negative underneath and we're taking an odd root, then I should have a negative number for my answer. So let's start small. We know it can't be 1, so let's check 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times another 2 is 32. So the 5th root of negative 32 would be negative 2. In example 2, I want the square root of negative 16. Now you guys remember these. If a negative is under the radical, then we factor it out with an I, and then simplify the square root of 16. And anytime we take a square root with a positive value underneath, we get a positive and a negative. Square root of 16 is 4, so this will be plus and minus 4i. If I want the two imaginary solutions. Otherwise, you would say no real roots. Example 3, the cubed root of negative 125. So negative 125, let's try 5s because it's divisible by 5. 5 times 5 is 25, and 25 times 5, so it would be quarters. So yeah, that does equal 125. Cool. But I have an odd root, and if I have an odd root, then I should have then I'm only going to have one answer, and it should take the sign of whatever's underneath, so I should have a negative value. So in this case, the cubed root of negative 125 actually is negative 5. Good job. And the 4th root of negative 243. Okay, again, it's got the negative, so there are no real roots, but we can simplify to get imaginaries. So let's factor out that negative sign first with an imaginary, both plus and minus, and then we're going to look at the 4th root of positive 243. That's definitely going to be divisible by 3. So 3 goes into 243 81 times. 81 is 9 times 9, and 9s are divisible by 3, so I'll do 3 times a 27. 27 is 3 times 9, and 9 is 3 times 3. Okay, so this is actually plus and minus I multiplied by the 4th root of 3, 1, 2, 3, 4, to the 5th power. Okay, so I have one full group of 3s. I've got 4 to make a full group, so I can do plus and minus 3I multiplied by the 4th root of just 3. And that would be the imaginary simplification of that particular example. If you wanted it in rational exponent form, it'd be a little crazy, but let's write it just for practice. Plus and minus 3I multiplied by 3 to the power of 1/4. And again, we're going to like that first answer that I wrote a lot better than we would the other. For these, make sure that you guys are practicing some problems on worksheet B. They're not super difficult, but you do need to practice and do your best to not use a calculator. Try to check yourself with it instead of having it simplify those radicals for you.